Welcome, everybody. Thank you very much for joining my talk today on GPU accelerated computing and optimizations on cross-vendor graphics cards with Vulkan and Kompute. We're going to have quite an exciting set of topics that we're going to cover today. We're also going to cover quite a broad ground, both conceptually and from a practical perspective. So I'm really looking forward to dive into it. If you have any questions, please make sure to share them, and I will be able to either cover them as we go or cover them at the end of the session. So let's dive straight into it. A little bit about myself. So my name is Alejandro. I am engineering director at this company called Saucedo Technologies. We built one of the most popular machine learning frameworks for deployment of models into Kubernetes. So focusing on deployment and monitoring of machine learning systems. I'm also the chief scientist at the Institute for Ethical AI, where I contribute to work streams and develop frameworks to ensure the responsible development, design, and operation of machine learning systems. And I'm also governing council member at large at the ACM. So let's set the high-level objectives for today. We want to cover, first of all, some intuition on parallel processing and why it's an attractive area to delve into. Then we want to set some insights to build kind of an intuition foundation on GPU computing through a simple set of analogies that will, of course, not be 100% sound, but it will provide us with some heuristics to get ourselves thinking in the mindset required for GPU computing. Then we're going to delve into the Vulkan SDK, the way in which this project is tackling and approaching the ability to really get a lot of value from cross-vendor graphics cards for both graphics specific and general compute. And then we're going to talk a little bit more about how we can leverage the compute framework to adopt this high performance capabilities within our C++ projects. Of course, we're going to cover a few hands-on examples, and at the end, I'll provide some references for people to be able to test by themselves on more advanced areas. So the first question that we want to set is, why parallel processing, right? And more specifically, parallel at the GPU level of processing. And there are a couple of motivations. So first of all, there has been a lot of interesting work and research, as well as practical applications that has shown that a lot of the functions, a lot of the logic, a lot of the work that us as practitioners develop can often be reduced into highly parallelizable stages. This is more often the case in computational and scientific type workloads. Where you have a lot of matrix multiplications involved, or in the context of machine learning, layer multiplication, et cetera. There is also ability to leverage, methodologies of approaching the sort of processing itself into the concept of micro batching, i.e., being able to process multiple inputs at a single clock speed, as opposed to leveraging that in sequence. And then finally, being able to break down fractions of each ensemble component across tightly coupled hardware, right? Like being able to take a single computation and distribute it across not just one GPU, but multiple GPUs if the amount of data that is to be processed is really large. And of course, this is not only the intuition at the high level, but we have also seen some interesting trends, such as an increase of reported experiments leveraging GPUs, compared to things like CPUs or FPGAs, and then similarly scaling into multiple even further parallelizable areas with multiple nodes, as opposed to what could be just a single GPU or a single node with multiple GPUs. So this is definitely a trend that we're only going to see growing. And as practitioners, we can benefit a lot in certain applications. Of course, there is a subset of areas where this can be highly valuable. I do recommend checking out this very interesting analysis that actually explores how parallel and distributed processing, particularly in the machine learning space, has grown into the GPU side. Now, to set some now intuition into basically the mindset that we have when developing our day-to-day code for CPU and actually developing for GPU type hardware, it's actually important to develop that intuition about around the structure and the internals of the hardware itself, the graphics card. So often it is the case that with a GPU, you get significantly larger number of cores, and this is something that you of course have already built that knowledge. But in the more granular side, this is important because unlike in a CPU, the cores at the GPU level may be slightly less, let's call it smart, but are able to process significantly more instructions at the same time. And the way that you can think about the hardware itself is split into the concept of grids, blocks, and threads. And the reason why it's important to think about this abstraction is because you get trade-offs at each of these layers. And we will talk a little bit more about what those trade-offs are in terms of shared memory access, in terms of processing, in terms of atomic locks, as well as the grouping that can be hierarchical for you to be able to split your data to be processed. And further to that, many of you may have already been aware of the distinction between your CPU memory or your RAM and the GPU memory or the VRAM, right? These two types of memories are of course accessible through different mechanisms. And the interesting way to think about it, although this is just a heuristic, is for you to potentially think about this as two different services that you want to communicate in between, right? Most of the code that you often write will run in the CPU and will have access to what we can call the host memory. So this is the terminology that is used in the GPU programming space. So you're often using your host memory address space. However, if you want to process something in the GPU, you will have to make sure that the actual data that you want to use is, of course, copied into what we call device visible memory addresses, right? This is basically where the GPUs can actually perform the computations and access the memory itself. Now, if you remember, we were talking about the hardware structure, and to keep a mind map around that, the reason why it's important is because there are also different types of memory when it comes to the GPUs themselves. Of course, there needs to be one type of memory, which we call CPU visible or host visible memory. This is memory that, of course, the CPU side will be able to leverage to copy initially the data into the GPU. Now, of course, that will be a slightly slower, let's call it, type of memory because it's host visible. You will want, in most cases, to actually take that data from the host visible memory address location and copy it into a device only visible address. So this will become a little bit more clear down the line, but now you're starting to see how you will have to make some trade-offs depending on where in the GPU hardware you're performing these different computations. The only thing to think about at this point is that intuitively, or from that heuristic perspective, you're kind of interacting with the GPU as if it was a separate, let's call it, service, i.e. a service that you want to send data, you want to send instructions to action on that data, and then you want to retrieve the results from this other memory address space or this other service, right? Of course, that is not physically correct, but that's a good way to build an initial intuition that will help you move through some of the examples. Now, when we talked a little bit about the structure of the cores being divided into grids, blocks, and threads, and we talked a little bit about the different memory types. Now, the important thing is that there is also a relationship between this concept of threads grids and blocks and the type of memory that they have access to, as well as the different speed in which they can access that memory or that they can share memory itself. So you can see that a block in itself would have the ability to provide a thread in itself, per thread private memory. It would be able to provide also per block shared memory, and then it would be able to provide abstractions at the grid level so that you are able to introduce, I guess, computational configurations that would allow for different things. And again, I would recommend you to delve into the resources, as this is, of course, just building a high-level intuition as opposed to providing a complete deep dive. So now that we've delved into the complexity of or the intuition around the hardware, now let's dive into the motivations, right? Like, why are we even talking about the need to understand and also leverage the advancements in tooling that now allows us to take advantage of this hardware parallelization? And the motivations to set the scene are on basically needing to address the challenge of heterogeneity, right? There's a broad range of different, vendors that provide, even larger broad range of graphics cards, thousands of graphics cards with different hardware architectures. And of course, there is a broad range of tooling that does allow you to leverage some of those capabilities. So tools that historically have been highly adopted and popular are tools like OpenGL, like CUDA, like OpenCL, et cetera. And of course, the only challenge is that there are trade-offs with each of these different components. And more specifically, now we're starting to see not just the adoption of the need for parallel processing and GPU processing at the desktop level, but also phones are starting to adopt GPUs that are almost as powerful, if not more powerful, than some of the GPUs that you get with laptops, right? So that means that actually leveraging some of the capabilities that come with these GPUs is desirable. Now, of course, when it comes to heterogeneity, it comes with complexity in the ability to standardize the way that you interact. For us, we are in luck, as there is an initiative called Vulkan, and more specifically the Vulkan SDK, which has taken as a core principle and responsibility to be able to provide a standardized SDK that allows you to not only leverage the power of this heterogeneity of all of the GPUs that well, not all of the GPUs, but thousands of GPUs that are available, with the premise of low-level access and high focus on performance and interoperability, right? So a single SDK for you to be able to access and leverage this heterogeneous hardware that is at your disposal. And of course, the great thing about this is that it's not just a side project that was started and it's just competing with other different side projects. It is actually backed by this group called the Kronos Group, which also is the overarching umbrella of some of the other projects that you may have already come across, such as the ones we mentioned, like OpenGL, OpenCL, SQL, et cetera, which are other projects to definitely check out. A lot of really interesting things. And there is a lot of importance of having the backing of the different players and the different vendors, suppliers behind some of these resources to ensure that this interoperability is adopted and it's not just another standard to set a standard, right? That is going to be replaced by another standard. So that's something that we're very happy to also see the growth of that. Now, if we dive into a little bit about the Vulkan SDK, of course, it has a lot of advantages and a lot of disadvantages. Let's talk a little bit more about what are some of the advantages of the Vulkan SDK. So the first one is that because it focuses on that ability to enable for configurability and interoperability and high performance, it exposes the very, very rich low-level access to all of the configurations that you would be able to, or that you would want to leverage at the GPU level, right? It also has given that it's a very low level side, it has a C-style API as the core interface for developing GPU applications, which means that you will have the ability to really, delve into the nuances, and we will see what that actually looks like in practice. It provides you with a tool that is backed by a broad range of top players who are leading the development of this framework, right? It has the backing from a large number of very kind of renowned and present players, and it's highly compatible across different platforms, across mobile GPUs, different suppliers, etc., etc. Now, those are some of the great advantages. Now let's actually look at some of the disadvantages. The first disadvantage is that it's very low level with rich access to components, which means that you have significant risk of shooting yourself in the foot, right? You're really delving with access to this heterogeneous hardware to optimize it to the extent that could be graphics card specific, right? So even though this means that you can get every single bit of performance, that means that also you have to deal with requiring or needing to get every single bit of performance. Another disadvantage is having that low level and rich access to components. It has that C-style API as core interface for developing GPU applications, which means that when you look at, and when we will delve into the C-style API, there is a lot of domain knowledge that needs to be built for the application developers, or even more specifically for the framework developers that are actually building an abstraction layer on top of Vulkan. And we're going to talk a little bit more about some of the projects that have adopted Vulkan and around how all of those projects, or not all, but a significantly large amount of projects have built their own similar boilerplate to be able to abstract some of that very, very low level API. Of course, a broad range of top players leading the development of the framework. That means that there's a lot of voices, a lot of opinions, a lot of agendas, and pulling kind of like towards different directions. So of course it has its advantages, but it has similar level of kind of like disadvantages. And finally, being highly compatible across different platforms, mobile and different suppliers, that increases the breadth of and complexity of the interface of the SDK. Having said that, even though we've covered some advantages that have very strong strengths, some advantages that the strengths can be the weaknesses, as we will see, the interface is a very, very strong, well-designed SDK that does allow for really great developer experience as you enable your programs with this general GPU processing capabilities. So now let's get an intuition about what does the Vulkan architecture look like? Like if we were to adopt Vulkan, what does it actually look like in practice? So as part of this C-style API, you get these different resources. So at the very top, you have the concept of an application. So this is your overarching resource that encompasses basically all of the different components that are created, spawned, managed, etc., etc. From this application, you can create an instance. So this is basically an instantiation of the application itself. This is a component that will be able to kind of like provide an ability to manage a subset of physical devices, of logical devices, of hardware and data. Below that, you have actually the component that encompasses a physical device. So this would be the ability to say this graphics card is represented by this object or this structure that has these configurations. And from that physical device, you can create multiple higher level abstractions that are referred to as logical devices, right? So if you want specific properties to be exposed for particular use cases, perhaps you may want some specifically focused on compute versus another one that you also want to leverage for graphics related stuff. That's when you would want to potentially have this separation if relevant. You would then have what is the concept of a queue. And this is really where I want us to remember that heuristic that we said before, that abstraction that we introduced of thinking about the GPU as a separate service, right? As a service that we can send instructions and send data, request some processing, and then retrieve the results. This is why I wanted to introduce that concept, because within Vulkan, within the GPUs themselves, having this concept of a queue is what will allow you to really consume and interface with this framework in an intuitive sense. So the queues themselves is where you are able to submit the work that you want executed in the GPU. And of course, intuitively, the next step, the command buffers specify the work to be carried out as an individual unit, i.e. things like move data, run these instructions, copy data, etc., etc. So you can see that now what we have in our mental mind map is this logical device with a queue where you send command buffers. Let's just remember some of these topics. To add a little bit more of an intuition on the complexity and not the complexity, the richness of the interface, you can actually have, as we've stated before, multiple divisions or multiple instances that refer to different physical devices or the same ones. And from each of the physical devices, you can have multiple logical devices. Similarly, each of the logical devices will have multiple queues. And actually the concept of a queue, this, as we will see later in the optimization stage, the queues themselves are actually hardware queues, and GPUs come with different types of queues, which have different properties. But let's park that for the moment. For now, we just have to think about this as the concept of a queues. Now, to reduce complexity, let's just look at this slice. So at one application with one instance, with one physical device and a logical device with a queue, right? What are the other components? And what are we missing right now? We've talked so far about being able to send instructions to a queue, but now let's talk about the data, right? We haven't talked about the data. So how does the data play into this? So the way that you actually have the data, you have the concept of a pipeline itself. So the pipeline is the core of the computation, right? Or the graphics computation. So this is what allows you to actually bind this queue with the commands that you want to execute, right? And I know that there's a lot of terminology so far, but this will all come together as we actually dive into the code. This will become much more intuitive. This is all the boilerplate to just introduce these concepts. But yeah, so the pipeline is the crux of your computation. The Vulkan pipeline, is core to the processing and is what you're able to bind the key components. You bind key components such as the instructions to run as part of a pipeline, right? So there is pretty much a one-to-one mapping between this concept of a pipeline and the instructions that this pipeline that you want to run with this pipeline. And every time that you want to do that, you would have to rebind the instructions themselves, right? So this is the code that you would want to run in your GPU, right? Then you have the concept of descriptor sets, which basically abstract the data, right? This is what allows you to say, hey, I want to connect this specific data to this specific pipeline with this code to execute it into the queue, right? So that's basically kind of like the intuition of this. And the way that you can define the different types of data, there are different, native data types, right? And we may or may not delve into the details, but just for the sake of explicitness, there are different types of, let's just call it native data types. Things like push constants, uniform buffers, storage buffers, and storage images. Each of them have different, let's say, cost of copy, a different cost of update, and you would use them in different contexts, right? For example, you would want to use a general, buffer when you would want to just define a piece of data. But perhaps if you have just a small component that you would want to update in a very, very efficient manner, you would use something like a push constant, right? Something that you actually define and then can potentially, update as required. So we may or may not have enough time to delve into some of the nuances, but the key thing to just remember here is that the way that Vulkan works is with the concept of the pipeline. The pipeline itself would bind the computational related components. As you would want to run something, you would actually bind your code or shader, your data as the descriptor sets with the command buffer. So this is basically what then you can send into a queue. And we will talk a little bit more about how you can then often just send data and then commands to copy data, etc., etc. Now, to make things a little bit more, I guess, complex, or actually this slide will make things more simple. In terms of the concept of pipelines, there are a broad range of different types of pipeline. And the two main sort of hierarchically top level concepts are the concept of a graphics pipeline or a compute pipeline. And this is just the type of attributes and resources that you can leverage as part of, and bindings that you can have as part of that pipeline. But given that our talk today is specifically about computation, like GPU computation, GPU acceleration, GPU optimization, we are not going to have to deal with graphics pipelines, which have a significantly larger amount of complexity that I have to emphasize. They are their own topic in itself, and there's like tons of really great videos about Vulkan or sessions and resources about Vulkan for graphics. This resource is about Vulkan for compute. And we're going to be using the compute pipeline, which contains the pieces that we talked about. So the compute pipeline that would bind the shader or the instructions, right? The pipeline layout, which would consist of the descriptor set and the data, right? So these are the components that we're going to be leveraging as part of this resource. Now, if we actually talk now in the process of a sequential life of a Vulkan program, what does that look like? Well, so you first have to set up that physical and logical device, right? That's step number one. You say, I want to use this GPU, my GPU in my laptop, and I want to create this instantiation of a logical device, which I'm going to be using for most of the operations. Then I have to actually compile that shader code, or those GPU instructions that we will see later on are in this language called GLSL. And we will be converting it into a machine code for the GPU to execute, right? So we have converted our code into GPU machine code. Now we have to create this compute pipeline, right? And as we said, from the compute pipeline, we can actually now start copying data, right? Because for us to compute anything, we first have to have some data in the GPU memory, right? So from the CPU, we would have memory address in the CPU side. We would then send a command to the queue to copy that into the GPU visible memory, right? So now we have some data in the GPU visible memory. Now we can start recording some commands, right? The commands that we want to do is we want to run a couple of multiplications, etc., etc. So the first command is actually to copy that data from what we were talking about being the host visible GPU memory into the device only visible memory. Why? Because we've said that those memory addresses will be more efficient, will be significantly more compute friendly once we actually run computations in the GPU side, right? So that's our first instruction that we send to the queue. The second one is to actually bind that code with the pipeline, right? So that's the first step. We're going to start binding that code that we want to execute. This could be a multiplication, this could be an addition, this could be something more complex, etc., etc. Then we bind the data, right? The descriptor sets are the thing that we mentioned that connect the data and the command, right? And then we actually dispatch that command, right? That's the command that runs the multiplication. So the GPU would actually run the multiplication against those memory addresses. And then once the multiplication finishes, we can send another command to copy the result from the device only visible memory to the host visible GPU memory, and then copy it in the CPU from the host visible memory into our RAM, where we can actually get the results, right? So that's basically super simple. Now we've understood the entire life of a Vulkan program, and it only took us 500 to 2,000 lines of low-level code, bug-free, of course, that is intuitive to actually delve into. And to be honest, once you actually delve into a hello world of a Vulkan pipeline, even though it's very verbose, it definitely is quite a nice flow, quite a nice architecture. But I mean, obviously, the elephant in the room is that it's 500 to 2,000 lines of code for the hello world of the raw Vulkan SDK, right? So, when it comes to complexity, you're already facing a lot of complexity from day one. So this is where we're going to introduce this framework called Kompute, the framework that we will use in the C++ side to interact with Vulkan by not abstracting, but augmenting the compute components of Vulkan. And this is the main reason why I wanted to focus the first half of this talk, giving a strong intuition of the Vulkan SDK, because the key premise of this framework is not to provide a high-level abstraction into Vulkan, but is to emphasize the compute capabilities of the Vulkan SDK. So that's the core, the crux of this. Now that you have this intuition of how you interact in this service-like manner with the GPUs, it will become very much easy for you to understand the actual code. The principles of compute is that it focuses on having dozens instead of thousands of lines of code to get started, but not to actually get to more advanced areas, primarily providing a transparent way of really accessing the internals of Vulkan. It augments Vulkan interface instead of abstracting it. And it has what we call a BYOV architecture. So bring your own Vulkan design. It's intended to play nice with existing Vulkan applications. And because of that, we wanted to have non-Vulkan naming conventions to disambiguate components, right? Because if we have things called buffer or pipeline, then it would just be, confusing of whether I'm using, compute things or I'm using Vulkan specific things, et cetera, et cetera. And what we're very happy about is that the compute framework is now part of the Linux Foundation. It's a project that now reached incubation level, and we are currently working towards graduation. Of course, some of the high-level features are the C++ interface, the main thing that we're going to cover today. It also has a Python interface for more domain-specific machine learning use cases. It has an explicit GPU, CPU memory ownership. There's actually a pretty interesting way in which this framework uses smart pointers to actually manage the GPU memory, and as well as the cleaning of GPU memory, which if we have time, we will delve into a little bit. It has granular access to what we will talk a little bit more, which are GPU queues. We've only talked about the Vulkan queues, but we haven't talked about the mapping into the GPU queues and how that allows us for optimizations. And of course, other things, like single header available and integration with mobile apps like Android, as well as game engines like Godot. So let's talk a bit about the Vulkan compute components, right? So whilst we had all of this broad range of components within the Vulkan SDK, now let's talk about the compute resources that group Vulkan components, right? So these are just grouping of components. And if we have time, we'll actually delve into what the grouping looks like. But instead of having the top level as an application, then with an instance, then with a physical device, et cetera, what we have is a top level compute manager. So this component is the resource that manages the Vulkan device and the Vulkan queues, as well as the application and the instance, right? So it also manages the memory at the GPU level. When the manager is removed, then the relevant GPU resources are also cleaned, but they are from an explicit rather than implicit manner. So the memory ownership is quite clearly stated. There is the concept of a sequence instead of a queue. So the sequence is a set of operations that can be executed as batch in a GPU that can be recorded and executed, right? Recorded and executed. And a compute sequence is actually responsible for the concept of a queue, as well as the ability to specify which queue you want to run it against. Then you have the concept of operations. So operations are an abstraction that allows you to group the concept of data and instructions, right? We talked a little bit about the pipelines, we talked about descriptor sets. So these are basically the components that abstract that combination of data and instructions, right? And you can see here, for example, that an operation can have just data, which is defined as a tensor, right? The core data unit component to transfer and process data via the GPU, via the buffers, right? The tensors themselves can actually have an operations like copy the tensor from my CPU memory to my GPU memory, or you can have operations that have both what we refer to as algorithms. This is the abstraction of a compute pipeline, the shader modules, i.e. the code, and then the descriptor set bindings for the data, right? So you can now start getting an intuition of what's happening under the hood within Vulkan around the way in which these components are able to group these resources and manage the resources themselves. So this is kind of a bit of an intuition of the components. So a manager, which has multiple sequences, each sequence which can have multiple operations, and then an operation that can have just data or tensor and algorithm. So those are the main things to consider. Now, let's talk about now, finally, delving into the code. So if we were to take the hello world of running a simple sum, instead of having to write, the large amount of boilerplate, the way that we do the interactions is with those higher level constructs. So first, we create our compute manager, right? We call it manager. That initializes all of the initial underlying resources like the device and the physical device. Of course, we will show some of the configuration that you can specify to be more targeted of what queues you want to use or what optimizations you want to use. After that, we create a bunch of tensors. In this case, a tensor, as we said, is just the data that we're going to want to use in our GPU. In this case, we're going to have an input tensor A with 3 numbers, an input tensor B. You can see here that the way that we are initializing it is through the manager. And the reason why is because they are being created within the device, right? Within that GPU that we specified. Of course, you can define the type that you want to use. You can explicitly say, I want to use a float, or I want to use an integer, I want to use a Boolean, etc., etc. So in this case, we have 2 input tensors. This is what we're going to be using for our sum. And we're going to define an output tensor, right? In this case, we initialize it with zeros, but for now, this is where we expect to extract our result. We then group those as parameters, right? So this would be basically just a simple array of shared pointers of tensors. And then we would be able to define the GPU code or shader, as we initially called it, the shader that we want to execute in the GPU. So this shader is very simple. This is basically the standard way in which you would provide the instructions to run to the GPU. This language is called GLSL. There are different variations. For now, just the only things to consider is a couple of things. We are expecting one input, right, of type float, which we're calling T tensor input A, another input of tensor input B, and then the output, which we call tensor output, right? Of course, there are some nuances that we have to define of what are the bindings, indexes in which they are going to be allocated. From that same perspective, this actually provides you a lot of the abstraction that you would require. And the only thing that we're executing in the actual computation is, this is a multiplication instead of a sum, right? So in this case, we're going to be multiplying our input A with our input B. Now, when we were talking a little bit more about the threads, blocks, etc., one of the things that we wanted to take into consideration is the structure of the GPU hardware. And the reason why that is important is because this is expected to be run in parallel for each of the indices that you define. In this case, these 3 components, these are going to be executed at the same, at a single GPU clock speed. And the things that we were talking about, if you wanted the execution to benefit from shared memory or atomic locks at a thread level, this is where you would want to define what is the sort of computational shape that you want to execute. And we will potentially see a little bit more about how you can define those things. Here, just know that we are defining a very simple, one-dimensional execution and we are sending basically what would be a, you know, the multiplication of these three elements at the same time. When we actually want to actually run this, the way that we would do that is we would define the algorithm, right, with this shader and these parameters, right? So we're basically saying we want to actually leverage the execution of these instructions with specifically these parameters, right? So we want to actually, of course, multiply the inputs and then store it in the output, right? This is what this actual instruction is doing. In order to execute it, we can, in this case, execute it using a anonymous sequence. So I'm only calling it anonymous sequence because later on, we will actually create different sequences. But here you can actually just create one that, you know, only has a life to run a single execution, and then it cleans all of the GPU and CPU resources. Here, what we're doing is we're running the creation of a sequence, and then we are recording 3 steps, right? The first recording that we are performing is what we talked about. We want to copy the tensors from the CPU memory to the GPU memory, right? So we then use this operation, tensor sync to device. So we're actually copying it to the device. As a first step, now that we have these tensors visible to the GPU, we can then dispatch the algorithm, right? So we record that algo dispatch operation with this algorithm. And then finally, when this finishes, we will have the results in the GPU side for our output parameter. So we can now send a record for an operation for the tensor to sync to the local memory, right? So now we're saying, I want to copy the results of, or I want to copy the latest of these parameters from their GPU memory equivalent to the CPU RAM, right? So I want to copy them from VRAM to RAM, and then evaluate those 3 operations that were recorded in the sequence. Once that is evaluated, when we actually print the value of our output tensor, we actually see the expected output, which is in this case the multiplication, which is 2, 4, 6. So that's basically it, right? All of the things that we were discussing, all of the underlying components that come at the Vulkan level. The reason why we wanted to cover all of those things in detail is to give an intuition, basically, of how then this works, even potentially at the hardware level, right? At the very lower level area for the application that we're leveraging. Now, so this is the hello world, right? This brings some interesting questions to follow up into. What are some optimizations that we can do? And before diving into the optimizations, we can first ask the question of what are the different ways in which we can run computation. So if we think about from the CPU side and the GPU side, or CPU time, GPU time, we have the first option, which is run a single command operation in sequence with a manager. So this is, imagine if we create 3 sequences, or we use one sequence, right? And we execute one operation at a time. We record it, we run it, right? In that case, we would record the copy to device, we run it. We then record the dispatch of the algorithm, we run it. We then record the copy back, we run it, right? So that is the most inefficient way, because you are actually waiting for that command to run, et cetera, et cetera. So it wouldn't be the most efficient way to approach it. The second approach is to reuse multiple operations in a sequence with the pre-recorded commands, which is what we did just now, right? We would record, in this case, 3 operations, and then we would evaluate them. And then in that same context, we can then record two new operations, and then we can dispatch them, right? So that's an approach that we can take. Another approach that we can take is that here we executed the commands in a synchronous manner by the CPU, right? Like we run the evaluation, the CPU waited for execution using a lock, and then actually received the response from, well, not the response, then retrieve the results. However, under the hood, the actual compute and Vulkan are able to use asynchronous evaluation of operations by default, right? Right now, we're only waiting because we've actually explicitly set a lock to wait until that operation is finished. But if we want, and we want to use the asynchronous commands that we will use in our next example, you can actually run the recording of the three operations. We would run an async evaluate. The CPU can do all the things, and then it can await for the response when it's ready. Similarly, it could record two more operations, run again a async evaluate, do other operations, and then retrieve or no, and then when it's ready, wait until it's finished, etc., etc. So this already brings a little bit of a way of thinking in how we're interacting with the CPU. Now, there is an extra consideration to take into account. There are some GPUs that now are enabling for what, and this may be a little bit like unintuitive at first glance, but there are some GPUs that are now enabling for concurrent, or more specifically, hardware concurrent execution of workloads, right? So first we were talking about a single execution being carried out in parallel, right? No question about that. A single execution is carried out in parallel. Multiple of those operations are carried out by the large number of cores, right? But when we submit a entire workload, right, the GPUs themselves can only run each of those workloads at every GPU cycle, right? Of course, you know, if there are multiple different programs actually submitting work into the GPU, some of them can be optimized. But to think about this is that if you submit multiple workloads to multiple queues, they will all still be executed in sequence, even unless there are some internal optimizations. However, we can actually leverage the concept of hardware concurrent execution through multiple GPU queues. And this is what we're now going to talk about, because there are some GPUs that have concurrent available queues, which means that you can submit multiple workloads, and both workloads can actually happen in a hardware concurrent way. And this gives you the ability to gain, you know, 2x, 3x, 4x performance improvements, depending on what are the hardware concurrent capabilities of your GPU. In the example that we're going to use, in my GPU, in my laptop, there is a possibility of having two hardware concurrent execution, which will allow us to actually show basically what a simple optimization could look like. Now, to get an intuition of what we're going to be doing in this current GPU, I have a set of different queues. I have a graphics queue, family index. I have multiple graphics queues. I have multiple transfer queues, and I have multiple compute queues, right? The difference between this type of queues is just the type of workload that they can execute. For example, the transfer queues, they can only transfer data. The graphics queues, they can do everything. And the compute queues, they can only do compute, right? So this is pretty self-intuitive. Now, the key thing is that I know that my GPU is able to support concurrent execution of one graphics queue and one compute queue, which means that even though I have like, I think 8 graphics queues or 8 compute queues, I am able to execute the graphics and compute workloads in you know, with a concurrent execution, right? So that's the key thing. And what that means is that now I can create a sequence for each of those respective queues. And that's what we're going to be doing, right? We're going to say, I want to create one sequence that runs on this queue, and I want to create another sequence that runs on this queue. That's what we're going to be doing. So what does that look like in practice? Instead of just creating a manager like we did, we actually can create a manager with the explicit device that we want to use. In this case, if I use device number 1, that's basically my GPU, right? And then I can specify which queues do I want to explicitly have available, right? Because the manager creates all of my device objects, Vulkan device objects, my Vulkan instance, etc., etc. So this actually initializes my queues for, in this case, the queue index 0, which is my graphics queue, and the queue index 2, which is my compute queue. So I now have within this 2 queues available that can execute in concurrent workloads, right? Now what I can do is I can create the same parameters that we want, but instead of actually having just a group of parameters, right? Remember that we actually had my parameter, my variable called params, and params consisted of my input tensor A, input tensor B, and output tensor, right? Instead of just having params, now we're gonna have 2 versions of params. Why? Because we want to run it in parallel, right? We wanna have 2 versions of params that we want to run concurrently, right? Once we have that, we can create, instead of an anonymous sequence, we create an actual named sequence, or more specifically, a explicit sequence object that has a relative index of the queue, right? So this index says, I want to create a sequence using the first allocated queue, right? Which is the queue of index, my queue 0, which is the graphics queue. And then I want to create a second sequence with the other one that I basically passed, which is basically my compute queue. So now I have this one running in my graphics queue, this one running in my compute queue, right? I can then actually run the same shader or the same code that I created and that I showed in the previous example. So I create that algorithm with the first parameters and an algorithm with the second parameters, right? And then I actually dispatch both of those components, right? So this assumes that I already copied the data accordingly, and now I just dispatch both of them at the same, well, not, okay, of course, not exactly at the same time, but I run both of them instead of just with the eval, I'm running it with the eval async, right? That means that the CPU doesn't wait for anything to finish, right? It just runs eval async on the first on the algo 1 and runs then immediately eval async on the algo 2. This would then run with hardware concurrency in the 2 separate queues, right? Which means that they actually run fully concurrently. And then I can actually run the eval await for the first sequence and the eval await for the second sequence, which then allows me to retrieve the results and print the results. So that's ultimately, the same paradigm, but providing more explicit distinctions on how you want to define the different areas. So that's a key thing to emphasize. The changes are, relatively minimal, but still very intuitive. And going back to the concepts that we talked about in terms of Vulkan, you can now have a mental map about how that fits into the underlying GPU-specific resources, right? So this is the key thing, is that now as practitioners, as C++ practitioners, if we want to start leveraging, GPU acceleration in some of our day-to-day workloads, having this intuition is more important than having just the frameworks, right? And building kind of that ability to think about the data and how that actually is related to the execution at the GPU level, that allows you to perform the optimizations required for you to get the most out of your optimizations. So of course, this is very, or not very, but relatively simple examples. There are much, I guess, more interesting examples as part of the tutorial section in the project, in the Kompute project. So we have some examples around GPU accelerated machine learning, where you're able to build a logistic regression classifier as a shader yourself, and actually run the train and inference in parallel, right next to each other. There's also integration with Android so that you can leverage the GPU of your Android device. And then there's also integration with some game engines like the Godot game engine by leveraging some of this ability to integrate GPU acceleration into your hardware. And of course, like any other open source project, always the mandate to get involved. We are very keen on continuing driving this conversation about cross-vendor GPU acceleration capabilities. So if you're interested, there are enough good first issues to get started with. You can also share your thoughts and suggestions if you find any areas that you would find interesting. And of course, we have some really interesting milestones as part of our roadmap. We want to continue building this framework such that it integrates as a backend of machine learning and scientific computing frameworks. We want to create a suite of operations with out-of-the-box commands. And we also want examples running across other different platforms. So there's a lot of different areas that you can actually leverage for these different components. And of course, just to emphasize, you can actually delve into a little bit more into the repo and find more resource in the documentation, together with some of the things that, of course, we didn't really get much chance to delve into, such as the memory management principles. And these memory management principles specifically specifying on how the underlying Vulkan components are managed and how they are explicitly defined. And mainly also having all of the different examples that you have at your disposal that provide you deeper insights of different data types or different memory access of the resources. I can see now, I think we have still 4 minutes left, a couple of interesting questions in the Q&A. So I'll just cover a couple of those very quickly. There's one question asking of why there was a mention of using shared pointers for the params. So ultimately, this is the current mechanism in which the memory management is provided, particularly leveraging smart pointers. So not only shared pointers, there's also weak pointers, as well as unique pointers that are used within the framework. If you're interested about that, you will get a little bit more details if you actually check some of the memory management principles and some of the examples and tests that delve into that area. There are other questions about like performance drawbacks using compute over the Vulkan API. So, the actual performance optimizations that you can get directly with the Vulkan API, of course, are not just specifically on leveraging the access to the Vulkan API, but it's the ability for you to build the higher level abstractions that then would allow your application developers to leverage from those. There are some, design decisions made in the compute framework that perhaps not align directly with your current project, like for example, the use of the standard library. However, ultimately we built it with a minimized set of dependencies, such that we don't interfere with the application level considerations. There's another question asking what's the suggested workflow for validating, testing the shader code, if it's basically just a string into the main code. So we actually do have a lot of interesting resources that allow you to compile this shader into what could be C++ headers that just have the binary as part of attributes that you can leverage through that, and you will be able to get a little bit more insights. We have a documentation page that talks directly about the point about shader management and optimizations. And then there's another question of whether it's possible to call C++ functions defined outside of the string in the kernel. So ultimately, this can be thought of in a way like providing a lower level interface similar to something like CUDA, right? You have your C++ code that runs on your CPU, but at this point, the code that is defined to run in the GPU is actually executed and defined by pushing it through the compute resources like algorithms, tensors, etc. So ultimately, the interface is basically that. So yeah, I mean, I think thank you everybody for these great questions. I'm more than happy to answer more offline on the Discord. But I hope that you enjoyed this session on GPU computing using Vulkan and Compute for cross-vendor graphics cards. With that, the call to action would be great for people to get involved through the GitHub, through our Discord, as well as through other of the open channels that we have with the Linux Foundation. So once again, thank you very much, everybody, and I hope you will enjoy the rest of the CppCon conference. Thank you all.